Pre-Calculus, Chapter P, Lesson P.1, Algebraic Expressions, Sets and Set Notation in Real Numbers. Please feel free to pause this video at any time to take notes as needed. First thing we're going to talk about today is the order of operations. You might have seen the order of operations before using the acronym PEMDAS, where the P stood for our parentheses, which also include our brackets, E as our exponents, M for multiplication, D for division, A for addition, and S for subtraction. In Precalc, we want to make sure that we're always following the order of operations correctly when we are evaluating or simplifying an algebraic expression. First off, when we're using parentheses or brackets, we always want to work from the inside and work outward. If an algebraic expression involves a fraction, we want to treat both the numerator, which is the top, and the denominator, the bottom, as if they are both enclosed in their own set of parentheses. Next, we always want to evaluate all exponential expressions. This will include roots and radicals. Our third step is to do all multiplication and division as they occur working from left to right, just like how we learn to read. Step 4 is to perform all addition and subtraction, again working left to right. So in this example, we want to make sure that we are evaluating the solution. Notice we have a couple sets of parentheses, so we always want to again work inside out. So we are going to start off by doing the 5 minus 7, which is going to give us a -2. We can go ahead and evaluate the other set of parentheses, the 4 minus 2, giving us a +2. Notice how we still have those brackets written around. And we're going to go ahead and bring down the 8 minus 3. Working from there, we can go ahead and evaluate the next step, giving us a +4, -2 times the -2, and then also going in and do 5 times 2, giving us a +10. Still using those brackets as that set of parentheses and bringing down the outside set. The next step here is we still want to work inside those parentheses, and so we're going to do the 4 minus 10, finally evaluating that last set, those brackets. If we do that 4 minus 10, we get our -6, and I rewrote that as parentheses, but you can leave it as a bracket if you'd like. And then we're going to go ahead and bring down the -3 and the 8. Oops, that's a little bit of a mistake there. Should just be one negative. And so if we take that -3 times -6, we get a +18. We take that +18 plus 8, we get a +26. Notice in our original problem, we had no variables, just numbers. And so that means there that our final answer should involve just a number. What we're going to talk about next is sets and set notation. A set is just a collection of things. In this case, since we're talking about a math class, we're going to be usually talking about sets of numbers. So sets of numbers contain elements or members. So each number that's contained in a set would be, in this case, an element. So like in this example here, 3, 6, and 91 are all elements of the set. Notice the 3 dots mean that the set goes on for infinite and then contains an infinite amount of numbers. Notice the set is always denoted using curly brackets. These are also sometimes called set brackets or braces. When we're working with sets, we want to make sure that we can use the proper notation for them. In this case, we call that set builder notation. So when we're talking about a set, we always want to make sure that set builder notation describes the characteristic of the numbers in that set. So for this case right here, if we're looking at the set where we have the bracket x, so that bracket means the set of, the x here is all x, and then we have this line. This line always means, in this case, such that, or we can read this as the set of all x's, or the set of all numbers, such that, then we add our characteristic, in this case, that x is greater than 0. So this is read as the set of all x's such that x is greater than 0. Or in other words, any value or number greater than 0. Please note here that x is just a placeholder. It's a variable. So it really could be used any variable that we want here. We could use q, p, fish if we want. It really depends on what we would like. And then some people also use colons instead of the lines. And so in this case, again, using that line or the colon to mean such that. Now, when we're talking about sets, we can also take a part of that set or a portion, and this is what we call a subset. This is written as A being a subset of B. The way you can think of that is that A is contained in B. Now, in the case where there is a set that is not contained in another set, or it's not a subset, we just draw a line through our little C there, which just means not a subset. So in this case, if that was set B and that was set A, notice that A is not contained in B, and so A is not a subset of B. Now, if we're talking about an intersection of two sets, A and B, is written as A, and then we have the upside down U, which stands for intersection, and B, is a set of elements common to both sets A and B. Another way of thinking that is that any element in the intersection must be contained in both set A and set B. So if we take set B, and then we also consider set A, then our intersection would be all the elements that was in their crossover. Let me illustrate that in a different color here. In this case, if we had set A, and had all its elements, and then if we also took our set B, and looked at all of its elements, any element or member that was contained in both sets would be, in this case, in the intersection of A, B. The opposite of an intersection is the union. The union of sets A and B, or written as AUB, is the set of elements that are members of set A or B. Another way of thinking that is that the union is all elements in A, and then also all elements in B, and then also that means also all elements in their intersection. So the union, it can be in either the intersection or just in one of the individual sets. So in our Venn diagram, it would be our entire shaded area. The empty set is a set with no elements. It is called the empty set or the null set and is represented by the Greek letter phi. In this case, we represent that by the circle with the line through it. FYI, in this case, the empty set is a subset of every set, which means that since every set contains really, in this case, nothing, then the empty set is contained in every possible subset of numbers. One thing to also note here is that the empty set is not 0. 0 is a number. It is not nothing. So we have to keep in mind there is a difference between 0 and nothing. So for our first example here is we want to find the intersection of the two sets here. So remember, intersection stands for, in this case, those elements that are shared between both sets. If we look here, we notice that both the numbers 3 and 7 are in both sets. And so if I call that first set A and the second set B, then our A intersect B would be the set 3, 7. Since these are both the elements that are found in both of our two sets. Now let's find the union of this. In this case, remember the union is going to be all elements in our first set or in the set of our second set. So in this case, if I call that first set A and that second set B again, then A union B would be all the elements, or in this case, remember, read A union B. In this case, then, it would be all our elements in the first set, so we can just go ahead and bring those down, 3, 4, 5, 6, and 7. But then since 3 and 7 are already in our union here, then we just need to include all those elements that are not have not been added to our union set that are still present in B. In this case, 8 and 9. So our union is containing all those elements that were in A and also the elements in B. We just do not need to repeat those that were already there.